a form of definition for the limit. The limit defined and given to us by um, um, Auguste Cauchy, Louis Auguste Cauchy, that is, the French mathematician, that a function defined on some open interval containing some number c, and the function may not possibly be defined at c, it does not have to be. And we said that L, capital L, is some real number. So for the statement that the limit f of x as x approaches c is equal to L means that for each epsilon positive, there exists a delta positive such that if 0 is less than the absolute value of x minus c less than delta, then we can find a suitable bound for the function and its limit, and we say that this bound is epsilon. So if we can put a boundary on the containment of x, any x value around the neighborhood of c, then can we also put a boundary around the limit for the function values? And what we mean here is that if we're on the x-axis and we have the value of c, we have a neighborhood here for this so-called x minus c less than delta. If you take that, we can expand that to mean negative delta less than x minus c less than delta. And if we take this value for c, and if you excuse me, add that throughout, then we have negative delta plus c less than x. Why is all that being erased? Use blue. So the absolute value of x minus c less than delta implies double implication that negative delta is less than x minus c is less than delta. If we add c throughout, we have negative delta plus c less than x less than delta plus c. So the neighborhood that we have here is said to be delta plus c, this area here, and then we have another neighborhood for the interval of negative delta plus c on this side. And so now watch this, because this distance that we say here is a distance of delta. So delta becomes the radius or radii. And the shrinking of delta, or even the extension of delta, you can do to be able to determine what happens with the y values for the function, that is the limit itself. Our goal is to shrink delta as small as possible. So in the shrinking of delta, and we want to get as close as possible as we can about this number c. And so what happens as x gets close to c? Well, if delta is so small, infinitesimally small, almost, then we say that x approaches c. And that is that if we can still find x values within a small neighborhood, a small delta neighborhood. Does that imply that the same thing occurs over for the so-called y values? So if you take this, then this is just by definition of the absolute value with this inequality. This is negative epsilon less than f of x minus L less than epsilon. No, delta is supposed to be epsilon. And if we add L throughout, this implies in both directions that negative epsilon plus L is less than the function less than epsilon plus L. And so now the same thing here occurs on the y-axis. So if you've claimed that L exists, some limit exists, then what happens above it and what happens below it? So below it, we say that this area is said to be the negative epsilon plus L. And then the area above is the epsilon plus L. And in this neighborhood, our goal again is to, as you shrink for the x value, as you shrink delta, does that also imply the shrinking of the epsilon? And so that we want to get as close as possible to the limit. Well, how are we getting there? We're choosing these so-called function values, right? So we expand this definition to look at this in both ways. So basically, the graph diagram that I just displayed is what is trying to be explained here. That as x approaches c, given some delta neighborhood about the x values, is it possible to shrink this measure, the absolute value, as a measurement or length? So can we make small this this delta radius neighborhood, and in the shrinking of that, does that also imply the shrinking nature about this so-called L value for the limit? So as the x values approach c, given within some delta neighborhood, does that imply that the y values also approach L given some epsilon neighborhood? And if that be the case, then we say that the limit exists. Well, let's see if we can prove that now. Let's take the first problem. We want to find the limit L, then use the definition, the epsilon delta definition, to prove that the limit is L. So notice here that if you plug in x to be 4, we have the limit of x plus 2 as x approaches 4 is 6. So we say by definition, this limit as x approaches 4 of x plus 2 is equal to 6 if and only if for all epsilon positive there exists a delta positive such that if 0 less than the absolute value of x minus, here c for the definition is 4, x minus 4 less than some delta implies that the absolute value of f of x minus L is less than epsilon. Now I'm going to replace the f of x with what it is. That's x plus 2. I'm going to replace the L with 6. So let me go ahead and just do that now. Just want to show you that. So here the function is x plus 2, and it's minus L, it's minus 6. And see that definition. Better erase this. This is not equal to 0. 0 is less than that. Zero is less than that. So we say, that is to say, that if 0 is less than x minus 4, less than 6, less than delta, then does this imply that the absolute value, simplify this is simply x minus 4. Well, here, the absolute value of x minus 4 is the same thing as the absolute value of x minus 4 over here. And so if we claim that this guy is less than some epsilon, but here we have the same quantity, the same measurement, so we can safely claim that epsilon is the same as delta. So here we simply choose or pick epsilon to equal to delta. And so what this simply says is that it doesn't matter for the restriction of delta. The whole object is, can we find a suitable delta? Now where do we get that language from? We get it from here. It says that for all, this is the symbol, for all, this is a symbol, there exists and this is such that. Okay. So the strong predicate here is the existence of a term. The existence of the term is predicated on if for all epsilon positive. So for any value, any positive value, can we find a suitable delta? Well, for this particular problem, it's very simple. It's very straightforward. I'll give you another one here that I'll make up in just a minute. Epsilon and delta, they come out to be the same thing because of the boundary. Remember, the absolute value is a measure. So this measure, the absolute value of x minus 4, all values of x minus 4, can we contain that by some number delta? Does that imply the same thing for what happens with the y values? Well, it does, because the absolute value of x minus 4 is there for delta, but then over here, the absolute value of x minus 4 is the same thing for the y values, less than epsilon. So if we choose the epsilon to equal to delta, that is, choose delta to equal to epsilon, then we have the limit to exist. I don't think there's any question there. Let me give another example. Let's look at the limit as x approaches 1 of 3x minus 5. Let's say x here will approach, let's say 3 and not 1. Doesn't matter, but plug in x to equal to 3, and we get just 3 times 3 is 9, minus 5, we get 4. We say by definition this is if and only if for all epsilon positive, there exists a delta positive such that if 0 is less than the absolute value of x minus c, here c is 3, less than delta, does this imply that the absolute value of the function minus the limit, can that be contained by a number? So here we have 3x minus 5 minus 4. Is this less than some epsilon? Excuse me. Okay. Well, we investigate that. So that is the case. If 0 is less than, if 0 is less than the absolute value of x minus 3 is less than delta, then the absolute value of 3x here minus 9 is less than epsilon, but let's see if we can simplify this. This is equal to the absolute value of 3 times parentheses x minus 3. And by definition of the absolute value, that this is less than or equal to the absolute value of 3, if I factor out that 3, times the absolute value of x minus 3. Well, the absolute value of this 3 is less than 3 times the absolute value of x minus 3. And notice that the absolute value of x minus 3 from what is given is less than delta. So this is less than 3 times delta. Well, you wanted this quantity, the absolute value of 3x minus 9, to be less than epsilon. So we have a choice for delta, that delta is equal to epsilon divided by 3. So we choose delta to equal to epsilon over 3. Now, it's somewhat strange, but to be honest with you, the proof now actually begins. The whole goal in engineering science is to be able to find a suitable delta. But mathematically, you want to start the proof now. So we say here that the limit 3x minus 5 as x approaches 3 is equal to 4 if and only if for all epsilon positive, there exists a delta, watch this, which is epsilon over 3, such that if 0 is less than the absolute value of x, basically you restate what you just got through going, but now you can lay claim to delta, which this is less than epsilon over 3, right? This implies then that the absolute value of 3x minus 5 minus 4, right? Here, notice how we simplify this, that this guy comes out to be, the absolute value of 3x minus 9. And so the absolute value, that is the absolute value of 3x minus 9, was less than 3 times the absolute value of x minus 3. And you recall that this is less than 3, and the absolute value of x minus 3 is less than epsilon over 3. So this is times epsilon over 3. So that is that 3 times the absolute value of x minus 3 is less than epsilon. And if you want to get jiggy with it, you remember that this right here came from the whole building of the absolute value of 3x minus 5 minus 4, and that's proven to be less than epsilon, with the choice of delta being epsilon over 3. So that's the actual way of, in terms of how we want to prove it. Now let's look at another problem. Prove the limit of x squared plus 1 as x approaches 1. If you evaluate that, then we have just 1 plus 1 is 2. So we say if and only if for all epsilon positive, there exists some delta. The whole thrust of this proof is to be able to find delta positive, such that if 0 is less than the absolute value of x minus 1, that's less than delta, then want to be able to show that the absolute value of x squared plus 1 minus 2 is less than some epsilon. Okay. So if that be the case, then, and notice what we're given. So we're given that the bound for x minus 1 is less than delta. To be able to prove that the bound for the y values is going to be less than, it's going to be contained, the bound of the y values with this limit, about this limit 2, said to be contained by some number epsilon. So if that be the case, then notice that we have the absolute value of x squared plus 1 minus 2, which is equal to the absolute value of x squared minus 1. This is equal to the absolute value of, just factor inside, x minus 1 times x plus 1. Now, by the so-called triangle inequality, this is less than or equal to the absolute value of x minus 1 times the absolute value of x plus 1. We already have a bound for the absolute value of x minus 1. It's said to be less than delta. So this is less than delta times the absolute value of x plus 1. We do not have a bound for x plus 1. So we take the bound that we do have, and you can choose a number for that delta to be able to find containment for this absolute value of x plus 1. We do not have an upper bound. See, there's an upper bound for the absolute value of x minus 1. It's delta, right? There's an upper bound for this x squared plus 1 minus 2 is epsilon, but we don't know what the heck the bound for x plus 1, which is inside of this guy, is being bounded by, right? So since we do not have a bound, is upper, by the way, bound for the absolute value of x plus 1, we will consider the absolute value of x minus 1 being less than delta, and here we want to choose delta to equal to 1. Just for this this case, for the boundary of x minus 1. And when we state, and we get to the end of this proof, we include in the selection of delta, there's also a choice that delta can equal to 1. So, and we choose delta to equal to 1. So this implies that the absolute value of x minus 1 is less than 1. By definition, that is, this is negative 1 less than x minus 1 is less than 1. What are we trying to do? We're trying to build a bound for x plus 1. So to convert this, what in the world? So to convert this x minus 1 to x plus 1, I need to add throughout this inequality a plus 2. So adding by 2 implies that we have 1 is less than x minus 1 plus 2 is x plus 1, and that's less than 1 plus 2 is 3. So I have an upper bound for x plus 1, that's going to be 3. So we say that this implies that the absolute value of x plus 1 can be bounded above by 3. So if that be the case, so we go back, so we have the absolute value of x squared minus 1, which is less than or equal to the absolute value of x minus 1 times the absolute value of x plus 1, and this is less than delta. For the absolute value of x minus 1, the absolute value of x plus 1 is bounded above by a 3, so this is times 3. So this is 3 times delta is set to be the bound for the limit, for the absolute value measure between the function and the limit value. And here, we wanted this to be less than epsilon. So we can choose here delta to equal to 1/3 epsilon, but there was another choice for delta, and that was 1 as well. And we can choose delta to equal to 1. We want to obviously take the smallest one. Why the smallest? The smallest value for delta means that the x values are getting close and close to the c value, which you want that to imply that the function values are getting close and close to the limit. You want to show that the limit exists. How to show that the limit exists? You want to get close to it. You get closer. So the closer you get to a thing or to a person, the more that you can determine what it is. And so as the x values get close and close to c, by making delta very small, well, delta and epsilon go together because epsilon is no more than 3 times delta. So when you put the restriction on delta, that also implies restriction on epsilon. And so here, for the choice of delta, we choose delta to be the minimum between either 1 or epsilon over 3. Okay. Thank you.